Welcome to the fourth and final part of Unit 9. In this part, we're going to do examples involving the law of universal gravitation. And the first one we do is a repeat of the one we did in part 2, where we're looking at what is the force that causes the Earth to orbit the Sun and how big is it. So you may recall from that portion that the force that causes the Earth to orbit the Sun is gravity. And now, instead of calculating this based on the fact that it's moving roughly in a circle at roughly constant speed, we're going to use the law of universal gravitation. And notice above, we're given the mass of the Earth, the mass of the Sun, and the distance between the Earth and the Sun. So we can just plug directly into that. So law of universal gravitation tells us that the force is given by the gravitational constant times the mass of the Earth times the mass of the Sun divided by the distance between them squared. So plugging in numbers, that's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, multiplied by 5.94 times 10 to the 24th kilograms, multiplied by 1.99 times 10 to the 30th kilograms, so the mass of the Earth and the mass of the Sun, divided by the distance between them, which is 149.6 times 10 to the 9th meters squared. And if you plug all those numbers in and do everything correct, you get a number of 3.5, oop, that's a 3, dreadfully sorry, 3.52 times 10 to the 22nd newtons. Okay, now this is the second time we've calculated this force. We've done it in two different ways. You might remember from number 1, we got a value of 3.53 times 10 to the 22nd newtons. And this time we got a value of 3.52 times 10 to the 22nd newtons. And now you're going to look at me and you're going to say, but Dr. Murphy, those two numbers are not the same, 3.53, 3.52. Okay, I agree. They're not exactly equal. But if you calculate a percent difference between them, that difference that you're looking is only 0.05%. It is tiny, 0.05%. Okay, so why are the two numbers not exactly equal? Well, the masses aren't exactly perfect, right? Mass of the Sun is not exactly 1.99 times 10 to the 30th kilograms. The calculation we made of the velocity for the other version might have involved some round off. There's all sorts of things that could make this be slightly different. But clearly the two methods of the calculation gave us numbers that are very, 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 very similar, for all intents and purposes equal. Okay, for our next example, this one's going to seem a little funny, but we're going to go with it. So you want to put an apple into orbit at the location of the moon. So what does this mean? So here's the Earth. Here is the moon's orbit. It's supposed to be a circle, best I can do here. Right, so there's the Earth, there's the moon. And in the same orbit, you want to put an apple to orbit the Earth. Okay, well, we can go online and we can look up how far away is the moon. So what is the radius of this orbit? And if you do that, you get 384.4 times 10 to the 6th meters. We can also look up the mass of the moon, which is 0.073 times 10 to the 24th kilograms. Mass of the Earth is 5.94 times 10 to the 24th kilograms. If you Google the mass of the apple, it gives you a range. At the upper end of that range, you get about 0.1 kilograms. And that's all the numbers we could possibly need for this. Okay. So remember that the gravitational force is what causes the apple or the moon to move in a circular orbit around the Earth. So we can say that the net force will take on the centripetal form. And notice that this mass here is the thing that is orbiting. So this would be the moon or the apple in this example. Okay. The net force is caused by the gravitational force, and the gravitational force is given by the law of universal gravitation. And I'm going to subscript that radius, and I have too many squares up there. The radius in the mv squared over r is the radius of the orbit, the distance from the Earth to the moon in this case. Now I can make some cancellations. One cancellation is that this mass, that orbiting mass, canceled. I also have an r squared on one side and an r on the other, so I can cancel one of those. And that leaves me with v squared equals g times the mass of the Earth divided by the distance, the radius of the orbit squared. So in general, I would say that the orbital speed is given by g times a mass divided by the radius of the orbit, where the mass that remains here is the thing that is being orbited. So the mass of the moon or the apple is the one that canceled. That's the orbiting mass. And the one that remains is the mass that is being orbited. This equation is on your equation sheet. It is part of equation 16. Okay. We can now plug in numbers for the moon, or the apple in this case. Both of them have to move at the same speed if they want to orbit at the same distance. So v is going to be the square root of 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. The mass of the Earth was 5.94 times 10 to the 24th kilograms. And I am going square happy on this particular one, so I wrote an extra square there as well. And let's extend the square root, shall we? There we go. And that distance was 384.4 times 10 to the 6th meters. And if you put that all in, you get 1,000 and that's not a very good 5, so let's try again. 1,015.2 meters per second. So for the moon or an apple or anything to orbit the Earth at the same orbital radius as the moon, it would have to move in the orbit at 1,015.2 meters per second. Now, we can do a check on this math really quick, because checks are always good. And that check is to remember, hey, this thing's moving in a circle at constant speed. Therefore, I can also define the velocity by taking the circumference of the circle divided by the time it takes to do one full orbit. So 2 pi r divided by t. Or I can rearrange this to give that t is 2 pi r divided by v. So that's 2 times pi times 384.4 times 10 to the 6th meters. Did I get that number correct? I did. divided by 1015.2 meters per second. And this results in a really large number, 23,790,94.2. Oh, not meters per second, seconds. Let's put some commas in and I'll read that number properly. So 2,379,94.2 seconds. If you do a unit conversion, you land at 27 and a half days. So it is going to take whatever is orbiting at the distance of the moon from the Earth 27 and a half days to complete one orbit. And if you think about this, 27 and a half days is roughly 1 month. And the orbital, or the time between successive phases of the moon, so to go from full moon to full moon, is roughly 1 month. So what I'm trying to say is there was a full moon on October 1st, 2020, and there is going to be a full moon on October 31st, 2020, which is 30 days apart, or roughly 1 month, 27 and a half days. So this calculation we did for the velocity of the moon does result in a number that is reasonable, is my argument. For the last example, we're going to calculate the acceleration due to gravity on the Earth, Jupiter, and the moon. This is equivalent of calculating the value of little g. So here is the setup of this problem. We have some planetary object, might be the Earth, might be Jupiter, might be the moon. I'm just going to call it planet for the moment. That planet has some sort of radius of the planet. And up above the surface of the planet, we have an object. So there's our, there went our object. There's our object. Let's say it's a ball. Now, if you go and you Google the radius of the Earth versus the radius of the moon versus the radius of Jupiter, what you find for these values is something on the order of millions of meters. So the radius of the Earth is 6.4 times 10 to the 4th meters. The radius of the moon is 1.74 times 10 to the 6th meters. The radius of Jupiter is 69.9 times 10 to the 6th meters. This ball is above that surface, and let's say it's less than 1 kilometer up. So 1 kilometer, remember, is 1,000 meters. So is 1,000 meters really going to make a big difference on a calculation that has another number that is in the millions of meters? Not really. So therefore, when we do our calculations here, all we're going to do is put in the radius of the planet. Okay. Other numbers that we may need along the way, we might want the mass of the ball. I'm going to go with a fairly hefty ball and let it be 1 kilogram. The mass of the Earth is 5.94 times 10 to the 24th kilograms. The mass of the moon is 0.073, it's a 7, times 10 to the 24th kilograms. And the mass of Jupiter is 1.9 times 10 to the 27th kilograms. Okay, now notice this ball isn't orbiting. It's going to be falling towards the surface, so it's in free fall. With that in mind, I can draw the free body diagram of the ball, being the gravitational force between whatever that planet was and the ball. If we're on the Earth, we would call this the weight between the Earth and the ball, but the point here is to actually calculate the equivalent of g. So F net is the mass of the ball multiplied by the ball's acceleration. That net force is caused by the gravitational force. And the gravitational force is given by the gravitational constant times the mass of the planet times the mass of the ball divided by the radius of the planet squared. And that equals the mass of the ball times the acceleration. Notice first, the mass of the ball cancels, which is why we can use 9.8 meters per second squared for all objects falling towards the surface of the Earth. So we have acceleration is g times the mass of the planet divided by the radius of the planet squared. So now let's go look at our three planetary systems. We have the Earth, we have the Moon, and we have Jupiter. The numbers are given on the previous slide, but I'll write them here as well. So for the Earth, this is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the 5.94 times 10 to the 24th kilograms, divided by that radius, which was 6.4 times 10 to the 6th meters squared, and that works out to be 9.7 meters per second squared, which is, given that we're approximating the mass of the Earth, we're not keeping that to all of its significant figure, or all of its possible figures, if you will. Same thing with the radius. Getting 9.7 versus 9.8 is pretty darn impressive, don't you think? On the Moon, we have 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass 0.073 times 10 to the 24th kilograms, divided by 1.74 times 10 to the 6th meters squared. And here we get 1.6 meters per second squared. And if you hear people say that the acceleration due to gravity on the Moon is about 1/6 that of the Earth, if you take 1.6 and divide by 9.7, you get about 1/6. And lastly, on Jupiter, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of Jupiter, which is 69. Oh, nope, sorry, that was the radius. 1.9 times 10 to the 27th kilograms divided by 69.9 times 10 to the 6th meters squared. And here you get 25.9 meters per second squared. This concludes the last part of Unit 9. In the next unit, we are going to switch gears and stop looking at forces and start looking at work and energy.